Welcome to our next lecture in the series on condensed matter theory. In this video I want to have a look at some examples of Ligand Field Theory and how to obtain the parameters that we have in Ligand Field Theory. So the hybridization or the hopping between the local impurity and the ligand orbitals from density functional theory. So the idea is to start with a mean field calculation and then derive from that the Ligand Field Theory parameters. And as an example material we will use nickel oxide. Nickel oxide has a rock salt crystal structure where you find a checkerboard order of alternating nickel and oxygen atoms in 3 dimensions. If we look locally, then you will find that you have here in blue your nickel atom, and your nearest neighbor atoms are 6 oxygen atoms, giving you a 6-fold coordination and a local OH point group. This actually is a very common building block for transition metal compounds, transition metal oxides, where you will find them 6-fold coordinated. Nickel is here in the periodic table and oxygen there. Now the oxygen becomes 2- for its formal valence, such that it has a completely filled 2p shell. The nickel becomes 2+, but we do not take these electrons out of the 3D A shell, out of the 3D shell, but we take them out of the 4s shell. The 4s orbital is much larger than the 3D, such that the 4s orbital is much more overlapping with the oxygen orbitals and can become emptied. And that leaves locally 8 electrons in the nickel D shell. If you do a mean field theory calculation, band structure calculation, in this case with density functional theory, then you find here in green the 6 bands are related to the 6p orbitals. We have not included, they are degenerate in spin, so that you have 3 orbitals left that you see, and in the high symmetry points they are degenerate. You have a local cubic point group, so the p orbital doesn't split at gamma. But then when you go to X, it splits into a 2-fold and a 1-fold degenerate band. Or at arbitrary k points, it splits into 3 bands. Then at higher energies around the chemical potential, you will find the d orbitals of nickel. The nickel is partly filled, and a d shell splits into T to G and EG orbitals. That of course only happens perfectly at gamma. Away from gamma they mix because you get lower point groups, but still they have largely the EG and the T to G character that you have, especially at the high symmetry points. So those are the band structures that we have for nickel oxide. Then we can have a look at the Wannier functions, and we pick them such that they are atomic-like for the d orbitals, and you indeed find that you get nicely atomic-like d orbitals top in a green gauge for the nickel-centered Wannier functions, and the corners of your cube are here the positions of the oxygen. Then on the bottom we have the p orbitals for the oxygen, so now the oxygen is the center of the magenta cage, and we have the nickel atoms on the corners. And you find that the oxygen atoms are actually quite modified compared to the atomic orbitals, whereas the nickel orbitals are basically the atomic-like orbitals. And we'll get to the reason for this. So we have the EG orbitals for the nickel that make sigma bonds, and we have the T to G orbitals that make pi bonds. If you look at the nickel wave functions, then in green here you see the atomic radial wave function, in blue the T to G, and in red the EG orbital. Now the EG orbital points towards an oxygen atom such that it needs to have a node at the position where the oxygens sit, and that indeed happens. So here we have the position of the nearest neighbor oxygen, and that's where you get exactly a node. The T to G orbital has already a node because of its angular dependence, such that the radial wave function does not need to go to 0. Therefore the radial wave function of the T to G is slightly more extended than of the EG. The EG is compressed inwards compared to the atomic wave function. If you now look at the oxygen p wave functions, as said before, they are not really atomic-like. They have these weird kind of tails here and additional nodes that on first hand looks a bit weird. Where could they come from? And now if you look at the atomic oxygen 2p orbital, then indeed it doesn't have these nodes, and it extends in the direct direction, seemingly a bit further. But if you then look here, the Wannier function crosses the line of the cage, whereas the atomic p orbital does not, such that actually the Wannier p orbital is a bit more bloated in that direction. Now, in order to understand where this oxygen p orbital comes from, you should realize that we started from our formal valences, where the oxygen becomes 2- and the nickel becomes 2+, because the nickel 4s is giving its electrons to the oxygen p. Well, that is the ionic picture. What happens in a real material, of course, is that you have your nickel 4s orbitals and your oxygen p orbitals, and they overlap, and therefore they make a covalent bond. And if you just look internally, then it is not a 1s orbital that has the same phase everywhere, but it is a 4s orbital where you have several nodes and changes of phases because of the radial wave function that we have in there. If you now make a bonding orbital between the oxygen p and the nickel 4s, it is this wave function that you get, and that indeed looks very much like the Wannier function that we have. So you should think of having a nickel 4s and an oxygen p, making a bonding-antibonding combination, and it is the bonding combination of the two that is occupied, and that then makes the what we call oxygen p bands. So it is these bands here between -8 and -4 electron volt that are the bonding linear combinations of the original nickel 4s and original p orbitals that then build the bonding linear combinations and the antibonding state that is up here. So you have the two orbitals making the antibonding going up, the bonding going down, the bonding becoming completely occupied because you started with the p orbitals at the Fermi energy and the s orbital below the Fermi energy, such that you then have indeed the bonding combination that now enters into the rest of our calculations, and which we will call happily the oxygen p orbitals instead of the oxygen 2p nickel 4s bonding orbital. The later is just too long to speak at each time. Instead of looking at a Hilbert space where we have both the oxygen s orbital, the nickel p orbitals as well as the oxygen p orbitals as well as the nickel 3d orbitals, we can also look at smaller Hilbert spaces. For example, look at the Wannier functions we include only the nickel d bands. Now you should realize that these orbitals that we have here are a result of having the atomic d orbitals that we had before interacting with the p orbitals on the oxygen, and the top bands are the antibonding ones, the bottom bands are the bonding ones. So the Wannier functions that you get when you focus on the smaller Hilbert space, which would be the Hilbert space in a crystal field calculation, are the antibonding orbitals between the d orbitals and the oxygen orbitals. And you can nicely see that the d to g orbitals then form antibonding combinations with the pi orbitals, or with the p orbitals that make a pi bond, whereas the EG orbitals make a linear combination with the p orbitals making a sigma bond. And you now also see that you have a node in between the character of the wave function on the oxygen and on the d side, and that is because you're in the antibonding states. So this would be the basis set that enters in a crystal field calculation. Now we can have a look just for fun also at the bonding linear combinations, where we focus on the p center. So this is an original p orbital centered at the oxygen side, and now you make a bonding combination in the direction of your orbital with a pz² orbital or a dz² orbital on the nickel side, making a sigma bond, and in the direction perpendicular to your p orbital, making a pi bond with xy-like orbitals. And here you see that you have charge density in between the p and the d orbital, because these are the bonding orbitals. I don't know in what kind of model you would use this as a basis set, but well, the pictures are nice and illustratively, especially seeing that these are the anti-bonding orbitals and those are the bonding orbitals that you can build from the set of Wannier functions where you include them both. And it is of course this set where your d orbitals become highly atomic-like, such that you can use the Ligand Field Theory approximations by adding the correlations locally and saying non-locally I'm going to treat everything in mean field theory. And especially when bands are completely filled, mean field theory is very good. So these are the bands that we have, and what we now want to go is to a model Hamiltonian that we can use and can derive a Ligand Field Theory Hamiltonian from. Now, the first thing that you should realize that in density functional theory, nickel oxide is a metal. We have states just below and above the chemical potential, such that you can make excitations with basically zero energy cost that change the electron momentum. So you can accelerate your electrons, and therefore this is a metal. Experimentally, nickel oxide is a pretty good insulator, both if you look at the optical gap, where it costs you 3.5 to 4 electron volt to make an excitation. So taking an electron out from one side and placing it on another costs you 3.5 to 4 electron volts, so that should be an indication of how large the Coulomb U should roughly be in your system. And then if you just look at the conductivity, the DC conductivity, you indeed find that you have a resistivity of about 10 to the 5 ohm per centimeter. Somehow my Greek letter disappeared and became a Roman letter. Now, that doesn't mean that the potentials are wrong or that the mean field solution is wrong. You shouldn't start to look for a different functional. In mean field theory, we have partly filled bands, and therefore this thing must be a metal. We have to go beyond mean field theory and include the local correlations that you can never treat on a mean field level. Locally, your state is not single Slater determinant representable. That said, the potentials that you have in density functional theory are actually pretty good. So we can use them to build on this our many-body model. So from our downfolded Hamiltonian, we also get a tight binding Hamiltonian, and we can then look at the on-site energy of the nickel orbitals, the on-site energy of our p orbitals, by just integrating the density of states, and then you find a given energy where these orbitals sit. Now, if we then look at the energy difference between the T2G and the EG orbitals, then the first thing that we can include is the non-spherical potential. And actually one should say that density functional theory includes all the effects that we are looking at, but we can now also separate them and see which part contributes to which energy splitting. And well, there is some splitting, but on this level of energy scale, it's extremely hard to find. So it is not a static potential that is important in energy scales that we have in solids. Actually, if you want to minimize the potential energy, then you should just take neutral atoms infinitely far away spaced from each other. If you really want to optimize the potential energy, not considering kinetic energy, then you would just put all atoms in a point charge on top of the nucleus, in which case you would have infinite potential energy. But of course, that requires wave functions that change extremely fast, so this also gives you infinite kinetic energy, such that in an atom the charge density already becomes more extended, giving you the orbitals, reducing the potential energy, but also reducing the kinetic energy. So increasing the potential energy because it was negative before, which of course in a solid you will increase the potential energy or decrease the loss of potential energy, and then reduce the increase the kinetic energy, decrease the potential energy. You bind because the kinetic energy is optimized at the cost of some potential energy. Now, we saw before that your wave functions for the T to G and EG have a slightly different radial part. And that's what you have here. The EG radial wave function has to have a node at a distance where you have the next oxygen atom, and therefore it is slightly pushed inwards. Because it's closer to the atomic nucleus, it will have a larger potential energy, so it should be lower than the T2Gs. It's closer to the nucleus. But then again, its derivative becomes also larger, so you have an increase of kinetic energy, and that will put the EG orbital higher again. Now, if you want to estimate which one is more important, the kinetic energy or the potential energy, then you can realize that the optimum between the two, with the total lowest energy, is the solution that we have in the atom. And you're pushing your EG orbital away from the solution that we have in the atom because you have an additional constraint, namely that you need to have a node where the next oxygen atom sits, because there your potential diverges, such that the additional constraint will always put the EG orbital above the T2G orbital. For the T2G orbital, the constraint is not that you need to consider the pole in this direction, but you have here the pole because of the next nickel atom, which is a distance square root of 2 further away. So this differences in radial wave functions because of divergences in your potential gives you a splitting of about half an electron volt. But it is a result of the cancellation of a kinetic energy and a potential energy that all both changes by several electron volts up to even Rydberg energy scales. You can easily change both of them as long as the difference stays roughly zero, and that's what's happening here. Now the p orbitals, if we just look at local interactions, they will just stay degenerate. The p branches to a T1U, so there is no change in energy between them. We now do not want to interact with all p orbitals separately. If you look at the nearest neighbor, then the hopping allows you to hop to 3 different p orbitals on all sides, giving you 18 different orbitals. So your tight binding Hamiltonian would be a 5 plus 18 is a 23 by 23 dimensional state or matrix. Now we can make linear combinations, and we can make those linear combinations by looking locally at your dx square minus y square orbital and see how you can hop. And in the y direction you can hop to a py orbital, different sign if you hop to the left or to the right, and in the x direction you hop to a px orbital. And if we now do not plot them as separate orbitals but get them close to each other and then add them up with the respective phases, then we see the ligand orbital to which you can hop. You have an anti-bonding state between the p orbitals because you have different phases looking at each other, such that you have a node between them. And also note that your ligand d orbital has some x square minus y square character of the d orbital on the nickel atom. And that is because we orthonormalize the ligand orbitals with respect to the starting orbital, and when you orthonormalize them, you mix in some part of the original atomic orbital. So in that sense, neglecting the correlations on the ligand orbital but taking them on the nickel d orbital is not perfect because of orthonormalizations, but good enough for many of the things that you want to describe. We can do the same for the T2Gs. Now an xy orbital hops to a py orbital in the x direction or to a px orbital in the y direction. Again, we have to look at the phases between them. Make sure here in this case that I have blue pointing to blue. We can do the same in the x direction. And now we look at the overlap again. You bring them close to each other and then you add the phases that we have. And now you see that here the orbitals with the same sign point towards each other, so that we here have a bonding orbital between the p orbitals, and that is the ligand orbital for the T2G orbitals. So our one particle basis has a d orbital centered on the nickel and a ligand orbital centered around the nickel but being large around the oxygen orbitals, because it's made out of the p orbitals centered on the oxygen atoms. And the same for the T2Gs. In one case we have an anti-bonding ligand orbital, in one case we have a bonding ligand orbital, such that you do find now splitting between the ligand orbitals due to the difference between being bonding or anti-bonding. Now you also can include the interaction between the ligand and the d orbital, just the hopping pp sigma and pp pi multiplied by the linear combinations and phases that we have. And that then gives you the bonding pi orbitals and the bonding sigma orbital and the anti-bonding pi and the anti-bonding sigma orbital. In ligand field theory, you start with these 20 spin orbitals in your basis and have a filling. In crystal field theory, you would focus on only the anti-bonding linear combination as your one particle basis set. Now, of course, we then have to look at all the many particle wave functions and solve the many particle Hamiltonian, because locally we want to include all interactions. And in the next video, we will then continue and see what the possible eigenstates are and what this then means for different observables that we can make. Have a look at some of the spectra that we can measure, so the response functions of our system. For now, I hope to have shown you a little bit where the parameters from a ligand field theory come from, what the orbitals are involved that we have to think about. And this is then, of course, an important ingredient for the description of many of the materials that we see around us. Thank you very much for your attention. We see each other later. Stay healthy.